Alright, let's come to the last topic of the chapter, and that is to see what is energy density within an electric field. We have seen what the stored energy is, but there is a very important relationship, and this will become really important when you do 375, and that is energy density of an electric field. I will get to this answer with a parallel plate capacitor. But this is true for any capacitive system where you have confined electric fields. So let's assume there is a parallel plate capacitor. We have created electric field E inside. This has a capacitance of A epsilon by D. And we created this by connecting a battery of V. So the energy stored is half CV square. We created electric field E. I want to involve this electric field. And we have said for parallel plate capacitor, this different distance between these two plates is D, and thus the potential difference is simply going to be electric field times distance, because electric field is a constant. So we substitute our various terms. We would get E square D square. I can write this as half. One D will cancel out, so I'm just left with AD epsilon E square. What is AD? AD is the volume of the capacitor. It is the volume over which E is confined. We have made E go in that volume. So the density, energy density, which is simply energy per unit volume, and in this case, electric field everywhere is a constant. All these are constants. So energy density in this case, we're going to write it with small u e, is simply going to be energy divided by volume, which is AD, and we get a very interesting result, half epsilon E square. So at least for parallel plate capacitors, we have seen that energy density UE is half epsilon E square. If you want, we can write this as half epsilon E E, but epsilon E is your displacement vector D. So this is half dE. And since D and E are in the same direction, we normally write it as a D dot E. That is your energy density in an electric field. Though we have done this for a parallel plate capacitor, this expression is the same expression for any arbitrary shape. Even if I have any arbitrary shape, of conductors and I have electric field, and I go to any point and make a small differential volume, then the energy density at any point is always going to be half epsilon E square. The energy which is present at that place would be the density multiplied by dV. This would be half epsilon E square dV. For calculation of capacitances, this is not really that useful. But when we do magnetic fields, we would define energy density in magnetic fields too, using something very, very similar. And over there, using energy density and stored energy can sometimes help us calculate inductances for some problems very easily as compared to first principles calculations we have been doing here. So keep this in mind. And then energy density plays a major role when you do electromagnetic waves. This is very, very important when you do electromagnetic waves in ECE 375. Right. This finishes our chapter for capacitances, and now you should be able to start attempting the problem sets which you have been given. Thank you.